An interesting but impractical method of generating prime numbers. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. Take the square of an odd number and repeatedly apply the quarter squares rule to it by subtracting a square and dividing by 4 to give the following tables. We see that the bracketed numbers combine by just the binary partition of an odd integer, the difference of which are the root of the corresponding square. Furthermore, we observe that when the integer we have squared is a prime, then the integer pairs resulting from the binary partition of that integer are co-prime to one another. However, when the integer is composite, then we find that the binary partitions plus the root of the resulting squares are not co-prime, and one is divisible by the other as shown highlighted red. Using the greatest common divisor as a test, we can check all the partitions to see if our original odd integer is prime or composite. The quarter squares rule is the Pythagoras theorem, so to see the prime and composite nature of the integers so visibly linked to it is to me truly amazing. I then proved that the findings were general by writing a prime finder program for precise calculator, proof by example. Compared to the prime macro that comes with precise calculator, my devised method was 1,330 times slower for the first 1,000 primes and 3,075 times slower for the second 1,000 primes than precise calculator's macro routine, which generates the first 1 million primes in just 33 seconds. I concluded that precise calculator's macro routine was based on repeated division, so wrote my own program. My repeated division program was 45 times slower than precise calculator's prime macro routine, which was not surprising as the prime function was programmed at a lower computer language level and therefore a lot faster than precise calculator's programming language. But it proved the point about repeated division. I also evaluated the benefits of reducing the size of the integer number field with mod 30 and mod 210 sieves of Eratosthenes, both of which gave the expected improvements. For sieves greater than mod 210, the increases were minimal and would have eventually resulted in time loss due to time spent retrieving the integers from their memory location arrays. Finally, to end this presentation is a video of my Texas Instruments SR56 programmable calculator, which I acquired in 1976 running the prime generator program based on repeated division, which reaches the 50-second prime value of 239 after 5 minutes. How technology has changed.